أوكي، إن شاء الله راح نبدأ اليوم في محاضرتنا لهذا اليوم في خصوص أو في عموم موضوع الintegrated reservoir characterization. اليوم محاضرتنا Seismic Outcrop Core and Well Logging Data Integration for Reservoir Characterization. Our speaker, Dr. Menmadi Milad, he has a Master in Petroleum Engineering from the University of Oklahoma, PhD in Geology, and he got it also from the Institute of Reservoir Characterization at the University of Oklahoma in the United States. He's currently postdoctoral researcher in the same school. So, Dr. Milad, could you please introduce yourself more and go ahead with your lecture?
Okay, well, thank you very much, Dr. Watak, for this invitation. Would like to thank everybody who's attending this presentation, and hopefully we will have more other presentations in the futures. So today I'm going to present to you data integration, reservoir characterization, and the scaling issue of the reservoir of different scaling for the reservoir characterization integration purpose. So as Dr. Watak said, my name is Menmadi Milad. I got my bachelor from Sirte University in Libya, 2006. 2013, I obtained my master's degree in petroleum engineering, basically reservoir engineering, fluid flow and simulation from the University of Oklahoma. Then I continued my PhD in geoscience department at the University of Oklahoma, in particularly geology department, in geology major, and I graduated in 2019. And currently I'm a postdoc in the petroleum department. So you can see me that I'm switching back and forth between petroleum engineering and geosciences, basically petroleum geology. So that's basically my area of studies. My specialties are integrated reservoir characterization and modeling. As you can see this in this workflow that I will talk further. Upscaling, 3D fluid flow simulation, and borehole image analysis and fracture modeling at different scales, from the fractures from the outcrops, fractures from the core, fractures from the borehole images, and integrate that with the seismic data for a larger reservoir scale. Then also I do statistical analysis and machine learning. I do well log interpretation and petrophysical analysis, seismic interpretation, seismic include the integrated reservoir characterization and modeling, upscaling and fluid flow simulation, borehole image analysis and fracture modeling at different scales, from the outcrop, from the core, borehole images, integrate that with the seismic. I'll focus more on the fractures today, and you will see some of the case studies. And machine learning and statistical analysis, well log interpretation and petrophysical analysis, and also seismic interpretation, seismic inversion, and the seismic attributes. So as you can see, this is the workflow that I have applied for my PhD studies. So I begin my work with the outcrop, as you can see it in this picture, then get as much data as possible from the outcrop to be used for the geological model. Also, I deal with the well logs, thin sections, and the borehole images. Interpret a lot of fractures from the borehole images and have different fracture sets, study their orientation, and integrate that with the seismic data with some structural attributes called most positive curvature or structural high, and most negative curvature, which is structural low, like you have an anticline or syncline. There are certain attributes for that from the seismic data. Then we'll go through some background of the seismic, but the seismic usually in the time scale, time domain, and convert that into the depth domain as they are from the well logs, and you need the velocity model for that. Then after that, I have the 3D property modeling, facies, porosity, permeability, fracture porosity, fracture permeability, matrix porosity, matrix permeability. Then populate the fracture model, in particularly discrete fracture network and fracture intensity, and then use all of the data that has been integrated in the geological model for the fluid flow simulation. Why are we doing all of that? This is not an easy work. It's not an easy task to do all of that. It takes a lot of time, and you are dealing with different scaling of the data. So you have the outcrop scale, you have the seismic scale in maybe in kilometers. You have a small scale of the thin sections. We are talking about the micrometer. So you need to gather more information and integrate that together. As I mentioned, it's not an easy task. Sometimes you integrate some of the data quantitatively, but many times you integrate your data qualitatively. So you build your knowledge, you build your geological background from different data type, and you use your knowledge to have a more realistic geological model. Once you have the realistic geological model, you run the fluid flow simulation. Why is that? The main purpose of this fully integrated, multidisciplinary, multi-scale surface and subsurface data. So the outcrop in the surface and the other data in the subsurface, in the reservoir. Why is that? For a successful exploration and development programs. Okay, so you from the static geological model, you have a good plan where to drill a well, in which formation you should drill. Okay, based on the lithology type, petrophysical data type, porosity, permeability, and so on. And you can run the fluid flow simulation for that particular zone or for that particular formation to have a good prediction about, to have a general prediction about the production, and that's what we care the most in the end, right? Do you hear me well? Hello?
Yes, yes.
Yeah, so go ahead.
Okay. So these are some of the publications that I have published, and I've sent those ones to Dr. Watak, and these are the papers, conference papers, and these are some of the posters and presentations that I have made throughout my PhD studies. Okay, so let me talk in general about the seismic data. Okay, because I'm dealing with the seismic and the well logs, so I would like to have a baseline general background about the seismic and the well logs. So the seismic, how it acquires. So what the seismic is that we image the subsurface. Okay, we image the subsurface. How we do that? As you can see in this picture, we have a track. It's called a Vibros. It has a vibration plate, and this is the surface. And before doing anything, you should distribute your GPhones, okay? And those GPhones, they have receivers, okay? GPhones and receivers. Sometimes they do have GPhones. Sometimes they don't have to have a GPhones if they have the track, okay? But let's say now you have the source of the energy, you have the receiver of the energies, okay? So what you do, and you have the layers in the subsurface, right? So what you are trying to do, have energy, okay? So basically you make, you apply a force, okay, with this vibration plate, okay, on the surface of the ground, okay? Then those waves goes into the layers, into the subsurface. Once it hits the first layer, the first boundary, it generates reflections, okay? And the reflections will generate on the, generate where there are change in the rock properties. So we have layer 1 has different rock properties than layer 2. Layer 3 has different rock properties than layer 2. And what I mean with the different rock properties, different velocity, different density, so those are the main thing. So once the energy hit the first layer, and it has let's say V1 and the density rho 1, it goes into the second one, and it has different properties. So what happened, it goes and reflects, okay? This reflection wave generated in terms of the acoustic properties, velocity and the density, and the receivers will receive that signal, okay, and record it in this track, okay? And definitely you'll have different acoustic properties at different angle gathered, okay? And you record all of that here, okay? And as I mentioned, this reflections is due to the change. This angle is due to the change of the lithofacies laterally, because you have different lithology type laterally, and you will have different lithology vertically as well. So as I mentioned, and then from there, after that, geophysicists will create the seismic trace which is the multiplication of the wavelet and the reflection coefficients. So this is the equation of the reflection coefficients, rho 2, density of the second layer, multiplied by the velocity of the second layer, minus acoustic impedance of the first layer, which is the multiplication of density by velocity, and divided by sum of both of them. Here is a model illustrates the illustrates the reflections of different layers when you apply when you apply a force or an earthquake. So you have shale, for example, if we have in the subsurface shale, sand, shale, sand, shale, sand. So the shale has higher velocity than the sand, okay, and so on, so on. Then we have the density of that, okay, density of the shale usually higher than the sand. So the multiplication of the velocity times density is the impedance, okay. Once we have this impedance, which is density times velocity, we apply this equation to get reflection coefficients, okay? And the reflection coefficients will be determined at the boundary between different layers, between two layers, okay? If you have high velocity into the low velocity, you will get a negative reflection coefficients. If you have and if you go from low velocity to higher bit velocity, you will have a positive reflection. Then you will have the wavelet, which is the reflected P wave on the rock boundary. Okay, this multiplication will create a seismic trace. Okay, a seismic trace has a peak and trough. Peak and trough. Peak usually to the right, trough to the left. That's the seismic trace. A combination of different seismic traces will generate a map like this, okay? You probably seen different seismic display, okay? Some of them wiggly traces. Those are the traces that I was telling you. This is the peak, this is the trough. This is the peak, this is the trough. Very similar to these things, okay? Where they are coming, those ones, from these processes and these processes. But for the people who might not be a geophysicist or who might not have a good background on the image, on the seismic image, might be a little confused because some geophysicists or geologists sometimes display the seismic data as this one, as wiggly, or as different colors, okay? And these color and these peak and trough represents the different properties of different layers, okay? Vertically as well as laterally, okay? Or sometimes people prefer to display the seismic data as a combination display, both the wiggly, this one, and this one, in order to have better reflectors, okay? So previously, seismic data used to be in a 2D, two dimension, X and Y, but lately, seismic data are acquired due to the advance in the technology. Seismic data is acquired on the 3D, okay, like this one. And what they call in the seismic data, they don't call X direction or Y direction. They usually say inline and cross-line. But keep in mind, inline, usually it's in the east-west direction, cross-line, north-south, okay? So you can say, you might think about the cross-line in the Y direction and the inline in the X direction, east-west. And also you might hear, so this is the inline, this is the cross line, and this is the time slices, okay? So because we are imaging the Earth, okay, or the subsurface actually, or the reservoir in particular. Let's say this is our reservoir. Okay, we drill a well all the way down, and this is the best area of interest. This is the pay zone. So you have the ability to see the continuity or discontinuity of the formation laterally, in the inline, in the cross line, okay, as well as in the time slice or in the depth domain, okay. Seismic data acquired in the time domain, in the time, how many seconds, okay, but you can convert that into depth domain. So you can have the same domain as well logs. Well logs, we have it in the depth, and the seismic can be converted from time to depth, okay. This is the another 3D image showing the different features of the rock, as you can see here, different layers, and yeah. So that's the seismic data. What we get from the seismic, we get a lot. We would be able to know about the structural. What I mean with the structural, anticline, syncline, because the layers in the subsurface not necessarily horizontal or flat bedded all the time. Sometimes they have incline, syncline, even in the subsurface, in the reservoir. You have many faults, and you would like to know about these faults, their locations, type of faults. Are they sealed fault or are they non-sealed fault? All of these informations are important for the structural geologist, and they have a direct impact on the reservoir performance. Not only that, if we speak from the stratigraphic point of view, what I mean with the stratigraphy is the layering, okay, layering, the change of the layer laterally and vertically. So we can get to know about the continuity of the layers or of the reservoir. How do we know those ones? We run different attributes. They call them seismic attribute. Those seismic attribute can show us more details about the stratigraphy, about the structural of the imaged area of the reservoir.
Excuse me, I have a question.
Sure.
I always find it very difficult to distinguish between 2D and 3D seismic images. To me, they look so much alike. So is there any particular sign on the image that helps us distinguishing them?
Okay, so do you see this middle image here?
Yes.
So in this image, it's a 3D image, 3D seismic image. So this is the inline, this is the cross line, and this is the time slice. Okay.
Yeah.
And the 2D image, you will not be able to have the time slice. So you'll have inline and cross line only. Okay. But for the 3D, you'll have inline, cross line, and a time slice. So that's the main differences.
Okay, but looking at the picture to the right, how can we know that this is a 3D seismic image?
Because this one, no, you can't tell about this one. Yeah, you cannot tell about this one right now, but I know this is a 3D image. I know this publication, and it's a 3D image. I could have brought another image from this study where they can display the time slice like this one.
Okay.
Yes.
Yeah.
Okay.
Thanks. Yeah. Thanks.
You are very welcome.
Excuse me, sir.
Sure.
What do you mean by you saying seismic attribute? What do you mean by that?
So these are the raw data, right? These are the raw data, and this is the amplitude, okay? So you have the amplitude, 3D volume of an amplitude, okay? This is a combination of different seismic traces, which is like, let me go back one more slide. So these wiggly shape, these seismic traces, you have many of them reflected at different angles, okay? Geophysicists will gather all of these, okay, in the entire area. Then you will have this volume. These are seismic traces. These are amplituded, okay? Then from this seismic data, okay, you would be able to generate different attributes, okay? What I mean with the attribute, so how I would explain the attributes to you. The attributes are mathematical equations, okay, where you would be able to use the different amplitudes, okay, and you see the variations between those amplituded, different colors, as you can see that here. And for example, the coherence amplitude, it's really good for most positive curvature and most negative curvature attribute. It will calculate the value of amplitude here, and it's, for example, let's pick this one, okay? So do you agree with me that the red trace, okay, is continue here and then discontinue here and continue again here?
Yeah, of course.
Okay. Okay, so so the value of the seismic trace or amplitude here is different than here and slightly different than here. Okay, so for the structural attribute, for example, the most positive curvature, where it's looking at the anticline area. So it would there is a formula for the most positive curvature to calculate to be applied for the entire seismic traces, okay? For example, this one, and you apply it and it will give you another shape, okay? It will prompt the variation of the seismic amplitude for this particular area. And you would be able to see what's really going on here. I'm going to show that with an example there. So there are some seismic attributes from this, some seismic attributes, yes, from the seismic amplitude, from the 3D seismic shapes that I showed you previously, and you run different mathematical equations to have different attributes. For example, coherent energy, reflector covariance, and each one convergence. Each one of those attributes has a specific functionality. For example, here, as I mentioned, the most positive principal curvature. It's really good for the karst feature. It's really good for the anticline high structural area. And so there is a formula to calculate that. Okay, so that's what I mean with the amplitude. Did you understand me?
Yeah, I got it, sir. Thanks.
Okay. This is the structure reservoir or for different layering. For Woodford Shale in Oklahoma, this is a shale structural map. This is a carbonate. This is another shale, and this is another. So so this is one of the attributes that I was mentioning. Okay, so you pick the surface of the of one of those amplituded. For example, this one, you pick this one, this and this and this, you continue and you stop here because there is a discontinuity and discontinuity most likely due to a fault here. And then you carry the picking, okay. Sorry, 1 second, please. So you will carry the picking because you think this horizons is a boundary, or this is a horizon is the top of one of the formation, okay, and you want to see how it changes, okay, and then you would be able to generate something like this structural map. In the structural map, you'll have the elevation. So this is structural high, red color, and the cool color is structural low. So this is another thing. So you can say here, hey, I have a high structural and low structural of my formation because the layers are not straight line in the subsurface. This is another seismic 3D seismic data where you have the inline and the cross line in the depth domain, okay, and all of these different colors represents different different layering or different formations, and you can see how that formation changes in terms of the elevation in the subsurface. Okay, here is you have high, here is you have low, low, high, and so on, so on. These are different surfaces or different tops of each formations. So are we good for so far for the seismic in general? If so, I can go ahead and give a general background about the well logs. Okay, so so you've probably seen the well logs, as you can see it in this image. So different colors represents different log type, and the different logs, different tool have a specific functionality, or we can obtain some information from it. For example, the gamma ray, it measures the radioactivity of the rock, okay, and this radioactivity level of the formations are of different formations vary from one to another. As a result, you will have different values of the gamma ray, as you can see it in the green. See this one. The gamma ray increases from right to the right from 0 to 200. Different formations has different gamma ray range. Okay, so this is the standard scale from 0 to 200. So as you can see here, we go down. We have relatively high gamma ray radioactive rock. This is most likely shaly formation. Then as we go down, the trend of the gamma ray reduces, okay, and we have this value continue low, okay, and this would be most likely clean sand or reservoir sand, okay, or reservoir sand, reservoir rock. And after that, you go and you have slightly a little bit higher, and again and again. Not necessarily you would have the same lithology within even the sand formation. Even inside the sand, you can have different laminations or different shale layering, okay, inside the sand. So for example, this one, you have a little bit of peak, might indicate of slightly high radioactive or high gamma ray, and you have again low, so you might have sand, shale, sand, a little bit of shale, sand, so you have an interbedded of sand and shale rock. And this is the caliper, okay, as you can see it in the black. So caliper helps us if there is a change in the diameter of the borehole, and if you have any changes, it's an indication of the washout. As you can see here, we have a washout in this particular formation, but in general, the borehole is a smooth. We don't have any washouts or breakouts inside. So this is the spontaneous potential, as you can see it in red. Again, here, usually you have the deep resistivity, LLD in ohm meter. You have shallow, and you have the medium resistivity. So sometimes the resistivity is 3 resistivity. So the shallow resistivity, it measures the resistivity of a certain radius from the well bore. Measure the resistivity of, I can't remember the number, but it's a very shallow, maybe 2 inches, I guess. And for the slow, for the medium, this is for the slow. Slow is the shallowest. Then the medium one, then the deep one. Deep one, you will measure the resistivity for the deeper in the formation. Okay. Because the shallow and the medium radius might be affected by the drilling fluid mud, and does not give you a good indication about the fluid type inside the formation. So resistivity is a good indication for the basically for the fluid type, and sometimes can be used as an indication for the lithology. Okay. And then here you have the neutron porosity and the bulk density, as you can see that. So this is the general, this is kind of like a main well log types that you usually have. Okay. The first thing when you have the those well log data, you need to display them in this manner. Okay, in this order. That's the standard method. Second, you need to see where is the different lithologies, shale formations versus non-shale formation. And here you would be looking first for the gamma ray, as you can see here. Here you have a low gamma ray, low spectrum, an indication of the reservoir rock, maybe a sandstone. But even within one formation sandstone, you might have different fluids inside the formation, right? Sometimes oil, sometimes gas, sometimes combination, sometimes 3-phase or oil, gas, and water. And you need to know about their contact, okay, their boundary. So as I mentioned previously, resistivity is a good indication for the fluid, okay? When you have, so the resistivity of the gas is always higher than the resistivity of the oil, and the resistivity of the oil is always higher than the resistivity of the water. Resistivity is just the opposite, the inverse of the conductivity, okay? So connectivity of the electrical current within the fluid. So as you can see here, we have a higher resistivity here, the highest here, but slightly higher here, okay? And you think there are 2 different types of fluid here, okay? But you are not sure if they are 2 or 1. And when you cross over the, when you lay both the neutron porosity and the bulk density, whenever you have a crossover, what I mean with the crossover, that means the neutron porosity reads higher than the bulk density. That's the crossover. Wherever you have this one, you definitely know this is this crossover is an indication of the gas. So from here, so from the resistivity, you wouldn't be able to really differentiate what kind of fluid is in there. But you can have a general background about it. You say, okay, I have different background of the fluid within this reservoir, but you are not sure about the exact boundary or about the type of fluid. But when you have the crossover, you are kind of almost certain that you have the gas in this zone and the oil in this zone and the brine or the water that has low resistivity in this zone. So it's always good to have the core data to validate your observations of the well logs. So the core data is hard data, and it gives you the true information about what you observe from logs. So here, talking about the core data. So here's one of the case studies where I integrated the log and the core data together for the different formations. So the focus would be on this carbonate in the United States, in Oklahoma. So as you can see, this is a shaly formation, okay, and this is a carbonate, has low gamma ray, and this is another shale formation that's really highly radioactive and rich with organic matter and higher TOC. And this is the deep resistivity, RT90. Sometimes they call it as LLD, deep resistivity, or RT90. And here we have the PE, lithological log, and we have the sonic. Okay, so sometimes we have the sonic, and this is the trying to make a crossover between the neutron and the bulk density. But as you can see here, there's not much of the variations. There's no crossover. That means there is one fluid, basically one fluid type within the entire formation. And this one is the different phases running through the self-organizing map of the machine learning algorithm, and different color represents different rock. For example, the purple is a wax stone. I have wax stone here and a wax stone here. The red one is the mud-dominated wax stone, and the green is muddy one. Okay, it's more of a shaly, but you don't in the carbonate deposition environment, you don't call it a shaly formation. You call it argillaceous mudstone. That means it's slightly highly radioactive as of compared to the other lithology type within the carbonate reservoir. Then this is the porosity value from the core plug. Okay, so those values taken from the core plug, they made a side core. They sent those side core samples to the lab to measure the porosity and its permeability. So the porosity increases in this direction, the permeability increases in this direction, and millidarcy unit. And this is the different lithology type in terms of the clay, quartz, and the carbonate, calcite. And this is the borehole image. Okay, that's how it looks like when they run the borehole image. And this is the another lithological profile based on the well logs. Okay, so in this case, you would be able to see if there is a relationship between the lithology type and its petrophysical properties and mineral properties as well. Okay.
Excuse me, sir.
Sure.
But how we can have a mudstone and the gamma ray indicates is low? From the picture, the gamma ray indications read very slow.
Here?
Hello? You hear me?
Yeah, I can hear you.
I was saying, how can we have a milestone here in the interpretation of faces, but the gamma ray is read very slow?
Well, the gamma ray, it reads slightly higher here. You see this one is slightly higher than those ones. Okay, so that's that's the mudstone, and the mudstone of a carbonate rock cannot be compared with the, for example, the mudstone of the shale. Okay, you have different mudstone types. Okay, so as you can see here, even this formation, it's highly radioactive. It's purely shale, but you would see different lithology. One of them would be a mudstone, and they have way much higher than they have way much higher gamma ray value as of compare of the mudstone of the carbonate. So when you talk about the facies classification or lithology type and the gamma ray value, you really need to think about where are you at, what's your reservoir? Is it a shale reservoir like this, or a carbonate, or a sandstone? Okay, so it does not necessarily, it doesn't mean that the mudstone of shale has similar or the same range of the gamma ray as of the mudstone of the carbonate, and similar to the mudstone of the sand. So it would be different.
Okay, it's clear now.
Thank you. So talked about the seismic in general, right? And talked about the well logs. Okay. Now, now I'm going to talk about the integration of those two different data type. Okay. So you have, so once you have, so why do we integrate the, so in general, how and why do we integrate the well log data with the seismic data? So different purposes. Okay, so you need to integrate the log to the seismic for the attribute of different attributes of the seismic inversion. Okay, basically seismic inversion, you have the well logs. Okay, and you have your seismic data. You tie both of them together. Okay, and from there you would have different other attributes like VP volume, 3D VP volume, VS. Okay, and the density volume as well from the seismic. Once you do that, and from there you can invert the porosity. Okay, once you have the porosity log at the well locations, you can also invert that, and you have a 3D porosity model within your reservoir area. And also you can have the lithology model. Okay, if you have a lithology log like this one, if you have a lithological log like this, you can invert that from the well locations, and after you tie the seismic to your well log data, you invert that, and you have a 3D lithological model of from the seismic. Okay. So here's an example where I conducted the seismic inversion. So in order to conduct the seismic inversion, you have to have a certain sets of well logs. Okay. You definitely need to have the bulk density. You definitely need to have the VP and VS. Okay. Once you have those ones, you use certain softwares. Here we use the Hamsa-Rosa software as it shows here. So this is the P-Wave This is the S wave, okay? So VP, VS, and this is the density. So what it does really, it makes it so, and then we have the synthetic and the actual seismic trace, okay? So the red one is the actual seismic trace that is on the same location of the well log where you drill your well, okay? And this one is the synthetic. What you are trying to do here, because you have the seismic in the time domain, the well log in the depth domain, you are trying to match the change of the size of the the synthetic seismic trace from the well log, okay, which is so this and the you are trying to match both the seismic with the well logs, two different traces coming together. As I showed you before here, you see those ones? We have the velocity, we have the density, we calculate the impedance, we calculate the reflection coefficients, and then we have the wavelength for the field, and then we have the seismic trace. This is from in the time domain. These are in the time domain, okay? We are trying to do the same thing. It's a very similar thing, not the same, but very, very similar. But right now, from the well log, from the well log, okay, in the depth domain. This is in the time domain. We're trying to duplicate this one in a depth domain. And that's what's really happening here, okay? We have the velocity, we have the density, we calculate the impedance, it's not shown here, and then from there, the software will calculate the reflection coefficients, and then creates this synthetic seismic trace. And as you can see here, the peak similar, almost matches to the trough, a peak of the seismic of the traces, synthetic seismic trace from the well logs. It almost matches with the peak of the seismic. Trough almost matches to the trough. It's really hard to have an exact match, but you are trying to do your best to match them. And you always need to take a look at the correlation coefficients between those two, between the synthetic seismic trace from the well logs and the actual seismic trace from the seismic imaging. So once you have that, you can have the 3D volume of the density. You can have the 3D volume of the S wave. You can have the 3D volume of the P wave. And from there, you can have the inversion, as you can see that. And you can generate the porosity. You can generate the lithology. And also you can have the fluid fill as well. If you have a saturation well log, you can invert that from the well locations into the entire seismic data. So that's the uniqueness of the data integration. So here showed you an example of integrating well log with the core data, with the image. Here showing the integration of the well logs with the seismic data and what we get from it out of that. This is an example of the impedance, okay? This is in a depth domain after converted the seismic data from the time to the depth, because we like to deal with the depth, right? And as you can see, different colors, different continuous color, and sometimes they have different variation in the color. So why it's varied? This is it varied. So as you can see, this is one of the wells that I showed you previously. So this is the well. This is the gamma ray. I think, yeah, this is the gamma ray, and this is the well. This is gamma ray increases in this direction, and these are the seismic traces. As you can see, that the wiggly shape, okay, combined with the color intensity of the color so you can have good display in that case. Okay. So I know this is from the gamma ray. From the gamma ray, I know the interval of the viola formation, viola viola carbonate, and I know the interval of the Sylvan shale. I know the Hunting carbonate, and I know the Woodford shale. So what I wanted to show you is that this formation has very high gamma ray, high TOC, high organic matter, but this one, carbonate, has low gamma ray, low, very, very low TOC. So the impedance is the multiplication of the velocity, basically velocity times the density of the rock. And different colors, green is low impedance, cool color, it has a higher impedance. So, and we can see the variation even within one formation. And this variation is an indication of the change in the lithology. And whenever you have a change in the lithology, you would have most likely a change in the petrophysical properties, like the porosity and the permeabilities and other formations. This is an example of one of the formations, the carbonate one, where I inverted the 3D porosity map. Okay, and here I wanted to. Hello.
Excuse me.
Sure.
How can I get porosity from seismic data?
Okay. You get that through the seismic inversion technique. It's a long process, but as I explained before here, first you should have the porosity log here. So once you calculate the porosity, okay, you have a porosity log here, right? Hello?
This is velocity.
Yes. So this is we can calculate the porosity from different logs, right? Like for example,
finite run or
yeah, there are different equations. We can calculate the porosity from the sonic only. We can calculate the porosity from the density log. We can calculate the porosity from the neutron. So for example, let's say we've calculated the porosity. We have another log here in another track. It's called the porosity calculated from the density, from the sonic, right? So yeah, first you need to make the seismic to well tie. Okay, you run and then you run the seismic inversion for that particular porosity log. Okay, so what it's really do, so it makes the software will create a correlation between the amplitude of the seismic data and the porosity value, okay, throughout your reservoir window, okay, and then come up with the correlation, and then it will populate that throughout the entire 3D seismic data. For example, whenever you have this certain amplitude from the seismic, it will use that particular equation to calculate its corresponding porosity.
Okay. Do you mean VSB? From VSB? In well, seismic in wells.
Yes. So you would have a seismic trace, right? In the depth domain. Let's say right now we tie the seismic to the logs, okay, and everything we have it in the depth domain, okay. Are you agreeing? Are you with me at this point?
I understand that you should have porosity from logs.
That's right.
Okay, and compared or correlation with seismic from VSP in Wales, because when I have 3D seismic for all areas, I don't have porosity for all areas, just
Yes.
in
Yes.
Wales.
That's true. Okay.
Yeah.
Okay. Okay. But you have these you have the amplitude, and you have the amplitude of the seismic, right? The amplitude, the seismic has a value, right? And also you have a VP. You have a VS. You have acoustic impedance. Okay. Actually, what the software does, it makes a correlation between the acoustic impedance of the seismic with the porosity. Okay, at that data point, and another data point, and another data point throughout the reservoir, and creates a correlation, a relationship between the acoustic impedance from the seismic and the porosity from the wall log. Okay, then you will have a 3D volume of the acoustic impedance. Okay, and whenever you have that acoustic impedance value,
I will calculate porosity.
Calculate the porosity, yes.
Okay. Thank you so much.
You are very welcome. And that's what we see here. This is the impedance. This is the impedance, and this is the corresponding porosity. Yeah.
Okay.
Okay. So keep in mind, logically, higher impedance value, you should have a low porosity, and vice versa. For example, this area has about 40 feet per second multiplied by the density of the impedance. And if you take a look at this particular, you have a low impedance here.
High porosity.
High porosity.
Okay, that is clear.
And actually, this is one of the examples that I'm showing how you obtain the porosity from the impedance. You can do similar technique, and you get the lithology model. Okay, and you can get other petrophysical properties as well. You know, like a saturation. You can have a saturation. You can have a porosity. You can generate the lithology model from the seismic. Okay.
That is mean we'll calculate saturation from density.
Well, I have to take a look back about the relationship. What seismic attribute should be used to calculate the saturation? I can't really remember as of now. But I think would be most likely from the density model. I think, but I'm not certainly sure.
Okay.
Okay, so so here I showed you the things that we obtain, the petrophysical parameters or the data or the results that we obtain from different data type, seismic, well logs, or the outcrop. Although I didn't talk much about the outcrop here, but I will talk about it in further case studies. Okay, but actually there is an issue with the resolution of this seismic of different data sets, right? Because of the different scaling. So here is an outcrop image, Here is in the centimeter scale. This is a well log. These are well A, well B, well C in a meter scale. We're talking about the vertical resolution now. And here is the seismic data, and also in the larger meter scales. Okay, so from 0 to 300, here from 0 to 12, here you can have the small outcrop or big outcrop in a centimeter scale. And you are trying to acquire data from this data type, from this data type, and from this data type, trying to integrate all of that. It's good, it's great that you integrate the data, you know, you get to use as much information as possible. But you always need to think about the resolution, okay? What I mean with the resolution, the vertical resolution, okay? You have different layers, and the horizontal resolution and lateral resolution as well, okay? So for example, the outcrop has a high resolution. Why? Because you would be able to climb throughout these rock features and study them at a centimeter scale, right? And you can document that and convert that documented data into the numbers and use that for your study, okay? So the core or the outcrop has a higher resolution, higher vertical resolution, okay? The well logs, I mean, it has a, I would say, it has still relatively high resolution, okay? But not, it's not compared to the outcrop or the core. And then you go further to the seismic data. Seismic data does not have a good vertical resolution. It has a very good lateral resolution, but not the vertical one. This is an example, okay, of a big outcrop. And when you do a seismic for this one, people has done a seismic for this particular rock, and they wouldn't be able to see those features in between, you know. They would see the boundary, okay, this is the boundary, this is the peak or trough, peak, trough, peak, trough, but you don't see this one. But you will have the leverage to see the lateral extension of those boundaries. So in general, seismic data has a very good lateral coverage, higher lateral resolution, but very low vertical resolution, okay? So here is another example. If you have
so sir, I have a question.
Sure.
So we can, by your say that seismic have a large scale, so we can't depend on the petrophysical distribution, right?
It's a good question. Yeah. So
I mean, we need to distribute the petrophysical properties geostatistically to build the model, geologic model, right?
well, here I have another way of integration. You would be you still would be able to rely on the seismic, okay, but for the lateral resolution, but not the vertical one, okay? And also you would be able to use the statistical distribution, mainly the histograms, for the vertical vertical resolution from your well log. Okay. Hello? Can you hear me?
Yes, sir. So you mean that in the vertical distribution we have to depend on the log data, but
Yes.
laterally on the seismic.
Yes, that's correct.
Okay.
That's correct. And just to build up on your question, it depends on the, and also depends on the, like on the stage of your reservoir, okay? Are you on the exploration stage? Are you on the development stage? Do you have many well logs in your area of study, or you don't? All of these things are important. If you are in the exploration stage, you most likely don't have a lot of wells drilled in that area. Therefore, you wouldn't have a lot of well logs. So in that case, you would rely more on the seismic data, okay? And but if you are in the development stage of your reservoir, you would rely on both. You combine both of them, the vertical resolution from the well logs and the lateral resolution, always good from the seismic data.
Okay, sir.
Okay. So just to envision the vertical resolution of the seismic, if you have this tower, okay, so you image your tower, so you most likely you'll have one change, okay, of the you'll have only like one change of your acoustic impedance and reflection coefficients. So vertical resolution is pretty low on the seismic data, okay? And here's another example. So you have the seismic and you have the wireline well log. So you see those wiggly things. The seismic data don't see that. It's kind of a blind, you know, it will see, okay, this is the change. These wiggly things represents different variations of the lithology here: sand, shale, sand, shale. So you can't, the seismic data cannot image or see that. And this is, for example, from the you can do a stratigraphic column from the outcrop. You see much details here. You see way much details than the facies from the well logs. So it depends. So higher resolution from the rock hard data, low vertical resolution from the seismic data. So that's the bottom line. But you would be able to, you would still need to integrate all of that together, okay? Preferably in a quantitative manner, but this is not the case all the time. So in that case, you would integrate your data even in a qualitative manner as well, by building your knowledge. Okay, I know this type of rock from the core or from the core or outcrop. So all of those previous slides that I've explained are just a general background of the data integration. Now I'm going to go further and deep into answering some of the research questions that I have studied throughout during my PhD studies. So these are the main research questions that I had and I've answered. The first question relies on the natural fracture distributions and how the distribution, the presence of the natural fractures affects the production and the fluid flow. And the second question is dealing with the upscaling, okay? Upscaling is changing when you have a geological model, 3D geological model, you can have different cell sizes, okay? And that's what I mean with the upscaling. When you have smaller cell sizes, you will have more data point of the lithology, petrophysical properties, more heterogeneous model, if you would call it. But you have to upscale your data. You have to upscale the size and the size of the geological model. And when you enlarge and upscale the size of the cell of geological model cells, you have to average the properties of petrophysical properties or facious properties, and when you average that, you will lose the actual heterogeneity. Okay, and when you run the fluid flow simulation for the upscaled models, many times you will not have a good prediction of the production, oil or gas. The third question is heavily rely on the geology with a focus on the lithology type and the depositional environment of sycamore formation in Oklahoma here. And the last research question is the relationship between the Woodford lithology, okay, shale with the and with the overlaying formation sycamore siltstone rock, okay. So this is the map. So my study shows, this is the location of my study area. It's in the United States, in the Oklahoma state. This is one, more particularly in this area, southern Oklahoma. And here I have different types of data sets. Okay, the triangle, where I have the seismic data, circle, core data, and the rectangular shapes are the three outcrops, okay, for the carbonate formation, and those are the other two outcrops for the Mississippian sycamore rock, siltstone rock, and also I have one subsurface well for the sycamore rock. So basically studied how many outcrops? 1, 2, 3, for carbonate outcrops, and 2 Mississippian sycamore. Those are 5 outcrops. And the subsurface data, 1 for the Mississippian sycamore, and the seismic data and the well location here, they are on the same area, seismic, and about 28 well logs, and I've studied 1 core. So that's gives you a general background about the data type and their location in Oklahoma. So let's begin with the first question, okay? So the first question was driven from the observations of the distribution of natural fractures, okay? This figure shows the borehole image. This is the mineral and lithological distribution. These are the fracture frequency, okay? So high, the longest one, this is the higher fracture. This is the fracture count. In this particular interval, you have, for example, 4 fractures, but this one is, you have nothing. This one for the total fractures, this one for open fracture, and this one is the just the dip of those fractures. Okay, so when I was picking the fractures from the borehole image, I had this image, and the question that come up to my mind with my advisor is that why do we have more fracture in this area, this stratigraphic interval, and this stratigraphic interval, but we don't have more fractures here, although they have similar lithology, okay? So that's something weird, and it's really important to study. Not only that, this is the stratigraphically, but also you have these golden color represents the fractures overlaid the lithology type in the seismic data. So you'll see the fracture variations laterally as well, okay? So the question is that why there is more fractures in some areas, but not in the other area. And in addition to that, the performance and production of some of the wells are vary, okay, although they are in similar area of in the same reservoir, okay, same formation, but you have different production rates. For example, this well A has this production flow rate, and this is well B. So the question here is that what are the factors that controls the natural fracture distributions? Why we have more here, nothing, to almost here, nothing here. We have more here, but almost nothing here. So why is that? What are the factors that controlling this? And what are the parameters? What are the fracture parameters that affect the fluid flow? Why we have higher production rate here than here? Is there a relationship between the presence of the fractures and production? So those are the main. This is the main questions that I have answered. So in order to answer this question, I have to predict the change. I have to find a way to predict the change of the fracture intensity. Here, more fracture intensity, a lot of fractures, but here a little bit. I have to find a way to predict that by studying two factors: change in the curvature and different lithology. Okay, and then from there, I built a realistic fracture flow model, fracture model, to be used for the fluid flow simulation to test its effect on the fluid flow. Why is that important? This can help improve the placement of a horizontal well. So you would drill a well in the more fractured area, and in a particular orientations, and also you can have more fracture permeability in this case, and that will have an impact on the production of a well. So this is the integrated workflow that I have used to answer this question. So I've started with the core, borehole images, outcrops, well logs, seismic interpretations, and the flow simulation. But the flow simulation results will be in the most likely will be in the further studies. I think Dr. Watak is going to organize another talk. I think I will focus more on the flow simulations and how that affect the production, how the fractures affects the production. From the core, you really can do a lot of study on the core. You can identify the lithology, the fractures, fill, like some of the fractures filled with certain minerals, and you can calculate the fracture intensity, and also the hardness. From there, once you have these results, you can really examine the relationship between the fracture, hardness, and the lithology. From the borehole image, you can study the fracture orientations, fracture aperture, and the fracture intensity. And from there, you can have intensity fracture intensity model, fracture intensity logs, and then you can use those well logs, integrate that with the seismic, and you have a 3D intensity model. You can do a lot of study from the outcrop, not only the lithology and the positional environment, but also you can study the fracture from the outcrop, measure its height, measure its length, measure the fracture intensity, measure the curvature. Okay, I showed you a curvature from the seismic. You can measure the curvature from the outcrop actually, and use that data to integrate that with the borehole image data and have the discrete fracture network model. And from the well log, you can do a lot from the well log. Okay, here in this particular workflow, I focus only on the fracture. Okay, but you can have more attributes or more results from this different data set for other purposes as well, for the lithology, for the petrophysical properties, and so on and so on. Seismic data, these are, so you would be able to pick the horizons, the surfaces of those different formations, and you can identify the faults. You can generate different seismic attributes: most positive curvature, K1, most negative curvature, K2. So K1 is an anticline, K2 an anysyncline. And you can have a 3D structural framework. It's really, really important. And you can use all of these data, all of these data, and build a geological model, 3D geological model, and run the fluid flow simulation and see what are the parameters that affecting the production. Is it the fracture height or the fracture length? Or so, are you with me? Do you hear me well, guys?
Yeah.
Okay. Do you have any questions? Do you have any questions so far?
No, that's clear.
Okay, good. Okay. So this is one of the outcrops that I used for the fracture studies. It's this is the outcrop, okay, and there are when you take a look at the outcrop, when you take a look at the rock from this picture, you don't see the change. You would see, okay, this is one formation, right? But when you come close to the rock, you would be and you take samples for thin sections and hardness measurements, and so you would be able to see the differences and the changes of the thin sections, different thin sections from those different layers. So what's the criteria of selecting the outcrop? Okay, so first and foremost, you always need to have the same subsurface formation, okay, that you study, if it's present in the surface or not. Okay, so you need to select the same formation of your reservoir, okay, to study its rock on the surface, if you have any. It's not it's not easy to find the exposure of the rock of your reservoir, okay, but if you do, you would be very, very lucky to have a better understanding and build a robust knowledge about your reservoir subsurface formation. So this actually, this formation is exposed in the subsurface, is the same as the formation is exposed in the surface, sorry, is the same as the subsurface, okay? Because previously from the well logs, we saw the mudstone, right? We saw the mud-dominated wax stone, and we saw the wax stone rock, okay? So this outcrop can be a good analogy to the subsurface formation or the the reservoir, since it's the same lithology. So that's a good thing. So for this rock, so we have the anticline, right? So we need to study the fractures at different lithology type, but also at different curvatures, you know. So those black stars represents the locations where I measured the curvature. What's the curvature? You see, this is the red anomalies. this is the most positive curvature. The blue anomalies is the most negative curvature. K2 blue negative, K1 red positive. Okay, so the harder the red color, the higher structure is. So for example, this color would represent maybe this value. This is in the subsurface reservoir, but this one, I'm just trying to connect I'm trying to explain to you the curvature attribute here, okay, and how it looks like, okay, here in the outcrop or from here. Here's the image. I think this is the better way. So here is the sink line, okay, would be represented as those blue colors. Here is the anticline. This area would represent those red colors, okay. So for this particular outcrop, I don't have much of a sink line here. I have kind of an anticline only, okay. I don't see much of the rock on this side. So what I did, I measured the curvature, okay. Curvature is 1/r radius, okay. So what I would do, I know the boundary of those layers, okay, different layer inside each lithology. I draw a circuit. Sorry, I draw a circuit here, and this circuit should be in contact with the circumferences, okay, and follow the shape of the dipping plane, okay. Once I do that, I measure the radius and calculate the curvature 1/r. So for example, calculate the curvature here, here, and here, and here. That's the first thing, to study the effect of the curvature on the fracture. And the second thing is that I take different windows of those rock at different curvature side. This is a low curvature, medium, high curvature, and I map those fractures. As you can see, this is the polygon. I map those fractures. Those are the traces of different fractures. And I usually take a polygon or an area of 5 feet by 10 feet, map the fracture, and calculate the fracture density or intensity here, okay? So how to calculate the fracture intensity is the summation of those traces, okay? The length, the summation of the length of those traces divided by the area, okay? So that's the fracture, and I do that for different windows, okay? In this, for different lithology. For the mudstone, here's the mudstone, here's the mud-dominated wax stone here, and here's the wax stone here, okay? And I do that for different areas, calculate the average fracture intensity, so I can have a good knowledge about the fracture intensity here for this formation at low curvature, for this formation at medium curvature, and for this particular formation at higher curvature as well. So I do that and calculate the curvature. Then I have a relationship between the curvature changes, as I can see. So this data point, curvature change at here, and this one would be the curvature at this data point. So calculate the curvature changes at different lithology type, okay, for different lithology. So here we have the mudstone, mud-dominated wax stone, and the wax stone. So here we have the fracture intensity, number of fractures per square feet. The first observations from this relationship is that you can see the fracture intensity increases with the curvature, right?
Sorry, sir, but how you measure the curvature? Can you repeat?
Okay. so we have the bidding plane, right? So do you see this, the boundary of this bid?
Yeah.
Okay. So let's say we are talking about this particular point. Okay. So you have the bidding plane. Okay. And then what you would do, we are talking about this particular one. So you have the bidding plane, and you would draw a circle that is in contact and parallel to the bidding plane. Okay. You draw the entire circle. Okay. Here. So you draw the entire circle like that.
Excuse me, Mr. Milad. Hello?
هاي الظاهر صار عنده disconnection.
I'm going so far.
Mr. Milad, can you hear me?
Yeah, I can hear you now. Yes.
Yes. I asked about the higher curvature and the oil fields in a crest, maybe?
Yes, that's right. Yes.
Yeah, okay. This is generals, the low curvatures and the flank.
Yes, that's true.
Yes.
Yeah.
The higher curvature and the crest.
That's true. Yeah. All right.
Yes.
Are you geologist?
Okay. Yes, I'm geologist.
Okay.
Okay, that's correct. Thanks.
Yeah, you are very welcome. Yeah. So so basically that's how one of you guys asked me about the attributes from the seismic. Okay, and I think I've answered him or her about the you have the amplitude, and from the amplitude there are certain mathematical equations, okay, to calculate and to calculate different attributes. So for example, this is one of the examples where you calculate the curvature, which is divided 1 by r, okay, and you get the radius from the different anomalies and different angle gathers, okay. So from
Excuse me, sir, but how can we determine the center of the circle in order to measure the radius?
So you determine. So you can So here is the thing, okay. You always need to have. You need to have the edge of the circle, okay, which is the circumferences, is in parallel to the boundary of the bed. Okay, so you need to stretch or shrink this circuit, okay, so that you make sure that the circuit is parallel and circumferences to the bed boundary. So this is the criteria.
Okay.
You imagine that, but at this particular point, definitely you cannot match that circuit throughout the outcrop. No, at this particular point, at this black point, you see this black point. So you have this black point here, and let's say this is the blue one is the boundary of the bed. So you need, and it's continue, it should continue. I just didn't finish it from here, from this side. And this is the circuit of the circle, okay? So you need to have a contact parallel contact between the circle that you are drawing and the bed boundary. So so after that, once you calculate the curvature at those different locations, okay, high curvature, medium, and low. So you already have calculated the fracture intensity here. For example, this fracture intensity represents this value. This one represents this one. And the average of those two windows represents this one. And so on until the crest. Okay. So from this relationship, we can see that although the distance between this data point and that one is about 120 feet, so we can see that there is an increase of the fracture distribution or fracture intensity as the curvature increases. Okay, for the three lithologies, for this one, and the other one. So this is the first observation. The second observation is that we see that the increase of the fractures would be more than 50% for the wax stone, from about 1.2 to about 2.5. It's more than 50% of the fracture intensity increasing for the wax stone. So here, that means there are two important parameters or two factors controlling the increase or decrease or the distribution of the fracture intensity. The first one is the structural or the curvature. The second one is the lithology type. Okay, so wax stone is a grain supported material, whereas the mudstone is it has less grain. It's a clay supported material. So from this observation, we see that from the outcrop study, we see that more fractures in the higher structural and also for the wax stone rock. So this is another outcrop where I studied the fracture as well, but the only difference in here is that we have the bedding plane is almost dips almost vertical. Okay, so we don't have a flat, it's almost vertical. So I did the same technique, but for this one I measured the gamma ray using the handheld, and also I've selected different points of different beds to measure the fractures. For this one, for example, and those are the different beds at different locations. For example, this one bed number 1, 2, 3, and this one is 12, as they are here, 12, 1, 2, up till 12. Then what I measured the fractures. Here, what I found different. I found fractures perpendicular to the bed and fractures parallel to the bed. Okay, so all the red fractures are perpendicular. The green is parallel, and I know the formation type and the lithology. And what I measured the fracture length and the bed thickness. Okay, this is the bed thickness, distance from here to here, and the bed length. So I have the dimension of the length and the thickness, and I've calculated the fractures, how many fractures I found them here. Then I've calculated their fracture intensity, which is the number of fractures by total length. Did that for all of the selected beds in the previous slides, and just draw the fracture intensity at those locations, trying to see if there is a relationship between the fracture intensity and the formation type. So this is the keel formation. It's has a lot of wood. It's and it's also grain supported rock. So it has a relatively higher fracture intensity as of compare of the other formations, so that we can see like the trend of the fracture density versus the lithology type. Then it's always good to plot and examine the relationship between the bed thickness and the fracture density. But for this particular case, we don't have a good correlation between the fracture density and the bed thickness. Usually, the thinner the bed, the higher fracture, the more fracture would be. So that's in general, especially in the unconventional reservoirs. But for this particular carbonate reservoir, we don't see this case. So here we examine, so here in this slide, I am showing to you the how do we use the outcrop fracture data for the subsurface fracture model. Okay, so you definitely from the outcrop you would have the ability to measure the orientation of each fracture set, okay, and measure their fracture length, fracture aperture, which is the fracture aperture is the distance, how much wide the fracture is, and the fracture length. So fracture length, you can have it from the top view or usually parallel to the fracture bedding, but the fracture height is always perpendicular to the bedding plane, okay? So, and then you calculate the statistical distribution in terms of its minimum, maximum, mean, standard deviation, and from that, you would be able to see the statistical distribution of the fracture length for each fracture set. As I showed in the previous slide, here we have 2 fracture sets. For other areas, I found 4, okay? And these are the direction of those fracture sets. Fracture set number 1, east-west, 2, north-south. Fracture set number 3, northwest, southeast. Fracture set number 5 is northeast, southwest. So once I get the statistical distribution of each fracture set for each fracture parameter, do the same thing for the aperture, and here is a summary of the statistical distribution. This table is very important to distribute the subsurface fracture for subsurface model.
Excuse me, sir.
Yep.
So here in these tables, we divide the fractures based on their orientation?
That's right.
Oh.
Yeah, that's what I meant by the fracture set. So this set 1 has different orientation, strike and dip. This one is another one. So and then I got that one. Then I use those statistical distribution for in the petrol model or other model, and populate the to build a more realistic subsurface model. So now here's the uniqueness of the outcrop study. Okay, so for example, the fracture height and the fracture length cannot be obtained from any other data except the outcrop, right? So so that's the uniqueness of studying the outcrop fractures. So those relationship cannot be obtained for the subsurface studies except from the outcrop. Once you have that, you can use it for the subsurface. So now I've talked about the outcrop fractures. Now I will be talking about the borehole image fractures. Okay, then if we have the time, I will go further into the core and show you the subsurface fracture model. But how are we doing with the time, Dr. Watek? Is Dr. Watek over there? Hello? Hello? Can you hear me, guys?
Yes, I hear me. Yes,
Yes,
I hear
yes.
you.
Is Dr. Watek over there, or?
Yes, yes.
Yeah, so Dr. Watek, how are we doing with the time? I can finish the fracture study probably in the next 10 minutes.
Okay, no problem, because we started at 4:10, so it's better to finish by 6:10.
When is the 6:10 would be? After how many minutes from now? Hello?
Yeah, we will be in 10 minutes. Like, you can finish in 10 minutes. Should be fine.
Okay. I mean, I can finish after that, slightly after, but I just need to go to the lab. I don't mind to.
So, do you want to finish now? It's fine.
No. I will finish. I will
10
finish
minutes.
on the same time. Just let me know about the time, okay?
Okay, I will remind you in 10 minutes.
Okay, thank you.
Go ahead.
Yeah, so I'll try to wrap up to finish this particular fracture studies at different scales. So I finished the, right now, I think you have a good background on the fracture studies from the Outcrop. Now, let me talk about the fracture analysis from the borehole images, okay? There are different tools of the borehole images, depends on the service company. So for example, FMI, it's a Schlumberger company. EMI, it's a Halliburton tool company. And the STAR, it's a Halliburton company. But here I'm not going to go into the details of those different tools, but in general, so those tools, they have something called bad nodes, okay? Those pads, they have different buttons, and they alternate the pads offset for each other. And those pads, they have a sensors, okay? And they would measure the resistivity. Now I'm going to talk about the FMI, okay? Different tools operates differently. And in general, you will have an image, whether that image is a result of the resistivity measurements on those sensors, or sonic velocity measurements from those sensors, or other type of measurement, okay? But right now I'm going to talk about the resistivity measurements, because that's what I am actually dealing with. I have 8 borehole images, and they are all FMI, and they are Schlumberger images. So what they do, once they drill the well, okay, they connect this tool, okay, with the drill pipe, okay, and they lower it down into, and they open those pads, okay, so that those pads can, and the sensors can be in a contact with the internal borehole, okay, and then they start logging from the bottom to the top. So they lower it up, they lower it, and they measure the resistivity. So one thing I wanted to tell you is that some of the FMI pads, some of the FMI tool, they have 4 pads or 6 pads, okay? the higher number of bads, the better image resolution would be, because they try to image the entire diameter, the entire interior diameter of the borehole image, so that they can image the features, like the structural features, the sedimentary features, the fractures, and so on, so on. So from the bottom to the up, they open the pads, they image that, they record the data, they gather the data together, as you can see here, and they put those data together, and they should be either in a 2D or in a 3D, and it will show you, it will image the internal features of the borehole. So for example, this one, it has a different color. This is the resistive, less resistive, and also you can see those features, and those features would represent the feature of the rock inside the borehole. So the borehole image has a very good high resolution, you know, in the inches scale actually. So you would be able to interpret those features if you don't have the rock, because coring the well is very expensive. So sometimes you don't really need to core the well. Instead, you need to image the well. Okay, might be much cheaper. So from there, you would interpret the boundary of the bed. For example, this bed, this lithology is different than this lithology. So this is the contact between those two different lithology. But now I'm going to focus my study on the fractures actually. So these are different samples from the borehole image, showing different types of the fractures. So in general, the natural fractures usually have a sinusoid shape, okay, and with a higher tip angle, okay, and you can see that the sinusoid shape is a conductive. That means the drilling fluid mud penetrates that fractures, okay, while you are drilling. So that's an indication of having higher conductivity, meaning that you have drilling fluid got into that fracture, meaning that this is an open fracture. Okay, so that's the open fracture. Sometimes you don't have sometimes you have a partially open fractures. How is that? So you would see some conductivity here, no conductivity here, but you would be able to trace that. Okay, higher conductivity here, higher here, but slightly here for that particular fracture. So this is one type of the fractures. I mean, yeah, one type of the fractures in terms of its filling, okay, whether it's filled or open. This is another image showing the showing the fractures. Okay, it has a sinusoid shape, but the color of that fracture, it's not conductive actually. You know, it's not conductive. It has a different color than the surrounding area, and this is most likely an indication of the closed fractures or mineralized fractures. So this is another type of fractures. Sometimes you have induced fractures. Okay, what's the difference between the induced fractures and the other fracture types? So usually I told you about the systematic shape and the sinuosity of the fractures. That's one criteria to pick the fracture or to identify the fractures, natural fractures from the induced fractures, or natural fractures from the bedding plane boundary of the rock. The second thing is that the other criteria is that the natural fractures usually do not cross into multiple bed, okay, or multiple layering, whereas the induced fractures usually go and cross through multiple layers. And this induced fractures is due to the drilling, okay? So those are not natural fractures. This is a bedding plane boundary, like this one. It usually cross different, no, the bedding boundary usually has
So, sir,
yes?
you mean by induced fracture, the ones are made by hydraulic fracture?
No, the induced fractures are the one that generated during the drilling.
Uh-huh.
Yeah,
Okay.
during the drilling. No, I'm not. Now I'm talking about the natural. I'm not talking about the hydraulic fractures as of now. I'm not talking about the hydraulic fractures.
Yeah. Okay, I get it.
Okay. Or sometimes you have small faults, okay, or small micro faults, fractures. So how to differentiate between the micro fault and the fault? The micro faults usually a fracture with a displacement of less than 2 inches. Okay, whereas the fault is a fracture with a displacement with more than 2 inches. Okay, and you can easily measure the displacement by stretching this image on the software, so you can measure that easily. Explained. I've talked about the different fracture types. Now I'm talking about how to pick those ones and how they do look like at the well location. So this is the map showing the location of the 8 wells that they have in the seismic data, and this is the polygon of the seismic, and those are the wells. Most of those wells are horizontal, and they acquired the borehole images and was able to pick the fractures here. This is a conductive fractures, like this one, conductive or open, blue one, and this one is partially open because I don't see the continuity of the soneous shape. And I pick those fractures, and it acquires some experience actually, and acquires some training to be familiar with those fracture types and picking them. Once you pick the fractures, because those borehole images are oriented, okay, when you upload your data into software, so whenever you pick those fractures, the software will calculate its depth magnitude for each one of them. So, for example, this blue has a higher depth magnitude, about 90. So that means they are vertical fractures perpendicular to the bedding plane. And you do that for the entire fracture data. Here, I'm just showing you a window, small window of the reservoir. Then you can display those fracture plates, okay, on the lateral horizontal well. So this is the lateral horizontal well, the trajectory of the horizontal well, and those are the fracture plane. Those are the partially open fractures. Those are the conductive fractures. So you do the same thing for the entire wells, and also you can easily plot the orientations in terms of the strike and the depth of each fracture, of each data point of that fracture on the ROS diagram. And from there you can see the